Hello everyone, myself Dr. Santavi Gundu. I welcome you all to this lecture of soft computing technique. This is the fifth lecture of module 7. So in module 7, we have already covered the introduction part of multi-objective optimization. We have solved few numerical questions by some methods of multi-objective optimization, just like weighted distance metric method, alpha constant method, etc. Today we will introduce the multi-objective optimization technique by using genetic algorithm. So many engineering problems involve multiple objectives that may conflict with each other. Have you seen some examples? A single objective optimization might optimize for one aspect while neglecting others, leading to suboptimal or undesirable solution from a broader perspective. In multi-objective problems, the goal is often to find a set of solutions rather than a single optimal solutions. This set is known as the Pareto front, which contains solutions where no objective can be improved without worsening another. These solutions are considered acceptable since they balance the trade-off between the different objectives. You have seen these facts. In a multi-objective optimization problem, we aim to optimize two or more conflicting objectives simultaneously. These objectives cannot generally be optimized independently, as improving one may worsen the other. A solution is typically evaluated in terms of Pareto optimality. A Pareto optimal solution is one where no other solution can improve one objective without worsening others. So you have seen some diagram I wrote in previous classes, just like these things. Let's suppose we are doing this problem that this is f1, we need to minimize it. This is f2, we need to minimize. If this is solution space, then the Pareto font or the optimal solutions Pareto lies in this region. Similarly for the others also. So we have studied these things. So genetic algorithms are naturally well suited for multi-objective optimization because they are population based. This means that genetic algorithms can explore multiple regions of the solution space simultaneously, increasing the likelihood of finding diverse and non-dominated solutions for complex problems. These solutions may come from non-convex, discontinuous, or multimodal spaces. So I told you that convex, these solutions you can say this is a convex, and this solution like optimal form like that. So this is a non-convex. Discontinuous and multimodal you have understood. So the crossover operations in a genetic algorithm helps combine successful solution structure from different parts of the populations. This can result in the generation of new non-dominated solutions that explore previously unexplored part of the Pareto front, improving the algorithm's ability to find optimal trade-off between objectives. So there are several multi-objective evolutionary algorithms. Few are non-elastic and few are elastic, means that best solutions will directly participate in the crossover for next iterations. In the crossover process for next iterations. So that is elasticity means for next iterations. We will study NSJ2 etc. So non-elastic multi-objective evolutionary algorithms. These are the few things are there. Vector evaluated genetic algorithm, vector optimized and evolutionary strategy, weighted based genetic algorithm, random weighted genetic algorithm, multiple objective genetic algorithm, non-dominated sorting GA, niched Pareto GA, elastic non-dominated sorting GA. That is basically NSGA to study these things. distance-based Pareto genetic algorithm, strength Pareto genetic algorithm, Pareto archive evolution strategy. So these are the uh, some methods of multi-objective evolutionary algorithms. So advantage of multi-objective genetic algorithms. So no need for prioritizing or weighting objectives. Unlike some optimization methods, multi-objective genetic algorithms do not require the user to prioritize or scale the different objectives, which simplifies the problem setup and avoids potential issues like improperly selected weights. Second advantage is popularity. Genetic algorithms have become a popular heuristic approach for multi-objective design and optimization problems because of their flexibility and effectiveness. A survey by Jones et al. Found that 90% of the multi-objective optimization approach aim to approximate the true Pareto front, with 70% of these methods based on evolutionary algorithms, including genetic algorithms. History of multi-objective genetic algorithms. The first multi-objective genetic algorithm was the vector evaluated genetic algorithm. You can write it VAGA, proposed by Safer. This was followed by a range of other multi-objective evolutionary algorithms such as niche Pareto genetic algorithms, non-dominative sorting genetic algorithm, strength Pareto evolutionary algorithm, and its improved version SPEA2, Pareto archived evolutionary strategy, first non-dominating sorting genetic algorithm, so that is NSGA2, and many others, each contributing to advancing the multi-objective optimization method. So first one is that vector evaluated genetic algorithms. So the vector evaluated genetic algorithm VEGA is a multi-objective optimization algorithm that extends the classic genetic algorithm, that is GFM work, to solve problems with multiple objectives. It is especially designed for scenarios where a trade-off between conflicting objectives need to be found. The primary advantage of VEGA, that is vector evaluated genetic algorithm, is its simplicity in handling multiple objective problems without the need for complex modifications to the traditional genetic algorithm structure. Now, VEGA approach. VEGA divides the populations into multiple subpopulations based on each objective. Each population is then evolved independently to optimize a specific objectives. Method. So step 1, the population of potential solution is divided as many subpopulations as there are objectives. So there are three objectives, then there are three subpopulations. There are two objectives, so two subpopulations like that. Each population is assigned a specific objective. For example, if you have two objectives, you would have two subpopulations each focused on optimizing one of the objectives. Step 3, the genetic algorithm is applied to each subpopulations independently. This means that the genetic operators such as selection, crossover, and mutation will evolve each subpopulation without direct interference from the others. Step 4, once the subpopulations have evolved, the final solutions are merged into a single populations. Since each subpopulations aim to optimize a different objective, the resulting solution represent a trade-off among the multiple objectives. Now, selection mechanism. VEGA uses a special selection mechanism to ensure diversity. It divides the populations equally across the objectives, ensuring that each objective gets an equal share of the population's attention. This prevents a single objective from dominating the search process and helps to balance the optimization across all objectives. Pareto optimality. After applying genetic operations, VAG's goal is to guide the search towards the Pareto optimal solutions. A Pareto optimal solution is one where no other solution is better in all objectives. That is, there is no other solution that improves all objectives simultaneously. Advantage of VEGA simplicity. The algorithm is relatively simple and requires fewer modifications to the classic genetic algorithm. Diversity. By maintaining separate subpopulations for each objective, VEGA promotes diversity and reduces the risk of converging to suboptimal solutions for a single objective. Second concept is that parallelism. Since each objective is handled by its own subpopulations, VEGA naturally allows parallel processing, which can improve computational efficiency in large scale problems. Disadvantage of VEGA convergence. The algorithm may face difficulty in converging to a true Pareto front in some cases. Each of the problem is highly complex or the objective are very different in scale. Second disadvantage is that limited explorations. The partitioning of the populations into subpopulations may limit exploration of the search space and the ability to explore global Pareto optimal solutions. Variants and extensions. NSJ2, that is non-dominating sorting genetic algorithm 2, a more advanced multi-objective genetic algorithm that builds on VAGA but introduces concepts like non-dominated sorting, crowd distance, and elitism to better maintain diversity and converge to the Pareto front. Summary of the steps of VAGA. First step is that initializations. So create an initial population randomly. Second is that division of populations. So divide the populations into as many subpopulations as their objectives. Step 3, evaluation of subpopulations. Apply standard genetic operators like selection, crossover, mutation to each subpopulations and evolve it towards optimizing its respective objective. Step 4, combining subpopulations. Merge the subpopulations to form a new populations that contain solution optimized for different objectives. Evaluate the population and check if the termination criteria, that is, as for example, a specific number of generations or convergence threshold have been met. Some example case. So consider a multi-objective problem with two objectives, minimize cost and maximize performance. Vega divide the populations into two subpopulations. One subpopulation focuses on minimizing cost and other subpopulations focuses on maximizing performance. Each subpopulation evolves independently and after a set number of generations, the solution from both subpopulations are merged to form a populations with solution that provide a trade-off between the two objectives. So that is some example use case. So example use case that we are suppose we are writing that f1x it represents to minimize this it represent cost, so we need to minimize it, and f2x is represents performance, so we need to maximize it. So suppose there are 10 initial populations. So that 5 will represent cost, that is f1x. So 5 subpopulations for f1x and another 5 subpopulations for f2x depending on their fitness. Then we will do crossover selection, crossover mutation here, and ultimately we'll combine these things. So uh, Vega is a simple yet effective approach for multi-objective optimizations problems. While it has its limitation in terms of convergence speed and optimality, it remains a useful algorithm for many real-world applications where multiple conflicting objectives need to be optimized simultaneously. Now, try to understand one numerical example. So, to provide a clear understanding of how vector evaluated genetic algorithm, that is VEGA, works in multi-objective optimization, let's walk through a numerical example. This example will involve a simple two objective problems and will demonstrate the process of applying VEGA step by step. So, problem description. First objective 1, minimize f1x equal to x square. Second objective, that the objective 2 is that maximize f2x equal to minus of x minus 3 whole square. The goal is to find a set of solutions that represent a trade-off between these two objectives. The optimization problems involves finding the best values of x that balance both objectives. So step by step Vega procedure. First one is initialization. We begin by randomly initializing a population of individuals. So let's consider, or we assume we have a population of 6 individuals with the following x values. So we have x1 equal to 1, x2 equal to 2, x3 equal to 3, x4 equal to 4, x5 equal to 5, and x6 equal to 6. You can take any numbers. So that is in step 1. In step 2, we need to evaluate the objective functions. So objective evaluation. We evaluate that two objective for each individuals. So that individuals are x1, 2, 3, 4, 5, 6. So f1x equal to x square. So 1 square is 1, 2 square 4, 3 square 9. Similarly 4 square 16. That is 25 and that is 36. f2x is minus of x minus 3 whole square. So put x equal to 1, that is 1 minus 3 minus 2 whole square, 4 minus 4, 2 minus 3 minus 1, that is 1 minus 1, 0, that is again minus 1, this is minus 4, this is 9. Now the objective function values for each individuals are: for individual 1, f1 equal to 1, f2 equal to minus 4; for individual 2, f1 equal to 4, f2 equal to minus 1; for individual 3, f1 equal to 9, f2 equal to 0; for individual 4, f1 equal to 16 and f2 is minus 1; individual 5, f1 equal to 25, f2 equal to minus 4, and f1 equal to 36 and f2 equal to minus 9 for individual 6. Now we need to divide 3 individual for f1 and another 3 individual for f2. So division of populations in VAGA. The population is divided into subpopulations. Each focuses on one of the objectives. We have two objectives in this case, so we divide the population into two subpopulations. Subpopulation 1 for f1x focuses on minimizing the first objective. Subpopulation 2 for f2x focuses on maximize the second objectives. The subpopulation size is 6, so we assign 3 individuals to each subpopulations. So subpopulations 1 where we'll find f1x is minimum. So if you go back, you will see that f1 is minimum for 1, 2, 3. So subpopulation 1 individual 1, 2, 3, and subpopulation 2 individual 4, 5, 6, that is another individuals. Now we need to do selection, crossover and mutation for each subpopulations. We apply these standard genetic algorithm operations. Selection: individuals are selected based on their fitness values. Since we are minimizing f1x and maximize f2x, individual with lower f1x values and higher f2x values will be selected. Next is that crossover. Pairs of selected individual are combined to form offspring. We can use simple crossover operator, that is the one point crossover technique. So you know these things. Mutation: random small changes are introduced to offspring to explore the search space. After performing crossover and mutation, the new individual are produced and the fitness values are recalculate it. So here we can say that x equal to 1, x equal to 2, x equal to 3. So that is sub for f1x. For f2x, that is x equal to 4, x4 equal to 4, x5 equal to 5, x6 equal to 6. So here you do the crossover selection, crossover mutation. Here you do the selection, crossover and mutation. So you'll get the new populations. Again, calculating the fitness function, and you need to do it. So here, re-evaluate and merge populations. After evaluation, the individual from both objectives, the trade-off between objectives F1 and F2 is captured by the merged populations. Termination, the process is repeated for the number of generation or until a convergence criteria is met. As for example, if the solution do not improve for a certain number of generations. Now example outcomes. So after applying the VEGA process, you might get a population. So the where after crossover and mutation, so suppose there is, as I said, x1 equal to 1, x2 equal to 2, x3 equal to 3. So keep at least x3 equal to 3. Now here you will get 1.5. From here you will get 2.5. So f1 x square is 1.5 whole square, so you will get 2.25. F2 is 2.5 whole square, you will get 6.25. F3 is 3 square. Similarly, for this value F2 also, that is minus x minus 3 whole square, so it is minus of 1.5 minus 3 whole square, that is minus 2.25. It is 2.5, so 0.05 whole square, 0.25 minus of that, and it is 0. Here also, so 4, 5, 6, so 4 square with these things, 5 square 25, here you get minus 4, 6 square is that 6 minus 3 or minus of that, so that is minus 9. Now the solution provides a set of trade-offs between the two objectives, such as minimizing f1x while also maximizing f2x. For instance, x equal to 1.5 offers a balance between these objectives, while x equal to 6 may represent a solution where f2x is heavily penalized to achieve a very low value of f1x. So here you can check that x equal to 1.5, you will get the minimum value is 2.25, but here it is not the maximum value. So you will see that our objective was minimize f1x and maximize f2x. So we minimize that 2.25, but there is the best value is not maximized, so it's okay. So rest all values are maximized. So for f1x 1.5 is better. Similarly, for x equal to 6, here where f2x is maximized but it is not maximized, so it is heavily penalized to achieve a very low value of f1x, because we want to find the minimum value of f1. So if we choose x equal to 6, but this is not good for f1x, so we need to find the trade-off between two objectives, so you can say that 1.5 is a better solution. Final remarks: the VAG approach will explore the search space by balancing the optimization of both objectives. The resulting populations will include solutions that represent different trade-off between f1x and f2x, potentially forming a Pareto font. The key point of VEGA is that it avoids a direct competition between the objectives by treating such objectives independently in its own subpopulation, allowing both objectives to evolve simultaneously but independently. So this numerical example illustrates a basic workflow of VAGA for a simple two-objective optimization problem. The algorithm can easily be extended to more objectives or more complex problems. So in conclusions, today we have understood the basic concept of genetic algorithms. Today we have understood the basic concept of multi-objective genetic algorithms, and we have understood one method. This is vector evaluated genetic algorithms. So there you have seen that we have done minimize f1x equal to x square, maximize f2x equal to minus of x minus 3 whole square. So now today question is that by using VEGA method, solve this objective. So minimize f1x equal to x minus 1 whole square and maximize f2x equal to x minus 5 whole square minus of this. So with any 10 initial populations. So if you have population 5 and 5, so try to solve these questions. So these are the references of today's class. Thank you.